So this afternoon we're going to take a short break from what you have been looking at, symbolic Python. We will continue with that after I put together some material on other things, well, other parts of symbolic Python which we need to know. But we're going to stop that a bit. We'll turn our attention to this chapter, which is the actual first chapter of the course, which is solutions to nonlinear equations. A nonlinear equation is basically an equation which is used to represent anything which is not a straight line. If something is a straight line, then we refer to that as linear, and an equation of a straight line is a linear equation. So straight lines, when it comes to finding answers and solutions to straight lines, that's much easier. But when it comes to nonlinear equations, sometimes it's easy, sometimes it's not easy. So that's what we want to look at, and how we can use computers to do something along the lines of looking for solutions. So, like I've mentioned, a nonlinear equation is an equation which represents anything which is not a straight line. Then a solution to an equation is basically a value of x where that particular equation cuts the x-axis. So basically, when you're talking about an equation, you're talking about something which is of this form. F of x is equals to something. In this case, when you're talking about finding a solution, then f of x has to be equals to 0. So the solution in this case is the value of x where this function f of x gives you 0. The process of finding a solution or a root, that is what is called root finding, and the solution which satisfies the value of x which satisfies this condition, f of x equals to 0, that is what is referred to as a root or a 0. An example of a nonlinear equation is what you have here. This is a quadratic equation. And of course, we know that there are a number of ways in which you can solve quadratic equations. You can do factorization. You can after doing factorization, you can complete the square. Then you can also use the quadratic formula. So those are ways of working out a nonlinear equation like a quadratic with pen and paper. There are also other nonlinear equations which you can work out along similar ways. For example, a cubic function. But there are other nonlinear equations which are not quadratics and not cubics, which are much more difficult to work out with pen and paper. For those equations which are more difficult to work out with pen and paper, some of them, it's not just that they're more difficult, but some of them you can't find the answer. It's impossible to find the answer with pen and paper. You have to use other methods. So you have to use methods which are known as approximate methods. And such approximate methods are what are referred to as numerical methods or numerical solutions, so that you can estimate what the answer is. In this case, you are not really trying to find these. You're not trying to find f of x equals to 0. But what you're trying to find is a value of x which is going to make f of x approximately equals to 0. Are we clear?
Yes, sir.
Yeah, you're trying to find the value of f of x which will make f of x to be approximately equals to 0. Once it becomes approximately equals to 0, then we are happy about that. Okay. Other times, so it's not just that you have got some equations which you cannot work out with pen and paper. There are such equations. So for such equations which you can't work out with pen and paper, where there is no analytic solution, then you need to use a numerical method. And it becomes even faster with these numerical methods when you use a computer. So we'll show you how to work out some of these things, how some of these numerical methods work with pen and paper, but with a computer, it's even much faster. There are also other cases where you have a bunch of equations which you can work out with pen and paper. The only problem might be that those equations are many and you need to find the answer very fast within a short period of time. Then you can use some of these numerical solutions because computers get faster and faster by the day. Now, for this to work, we have to make a couple of assumptions. In this case, there are certain assumptions which we are going to make. one of the assumptions we're going to make is that when you're trying to find these roots, or when you're trying to find these zeros, we are assuming that in the region we are interested in, we are assuming that this particular function you're looking at only has one root. Okay? But that might not be true, because there are certain functions, for example, a quadratic equation. A quadratic equation cuts the x-axis at two different places. So a quadratic equation has got two roots. When f of x is equal to 0, it has got two roots. That's not what you're looking at. What we are interested in are those functions which only cut the x-axis at one place. That is what is referred to as a function with a single valued root. So this is what we're interested in. In the case where we have got a function which cuts the x-axis in more than one place, like a quadratic or a cubic function, we are going to be interested only in a certain area. We'll be looking for the solution or the root only in a particular area, such that in that particular area we'll be interested in, there is only going to be one root, so that we can satisfy this assumption we are making, that our function f of x, or our equation f of x, only has one root. Are we clear?
Yes, sir.
There are certain functions which only have one root. There are others which might have multiple roots, but in the case where the function with multiple roots, we are going to restrict ourselves only to a small area, so that we can make sure that our function has got one root. The other thing we want to assume is that the roots which we are interested in are real. So these are real valued numbers. So we are not talking about complex roots. We are talking about roots which are actually floating point numbers. So we just make two simple assumptions. One, that the function we are interested in is going to have a single root in that particular area we're interested in. If it has got multiple roots, then that particular function will focus on a certain area, so that we only find the root which is in that particular area. Okay, so with these two assumptions, we are going to use two methods. One of them is referred to as a bracketing method. The other one is referred to as an open method. We're going to talk about what these bracketing methods and open methods are. Now, when you talk about bracketing methods, basically what you are doing is you have a very good idea that this particular function you're interested in, f of x, cuts the x-axis somewhere at some point. So what you do is that you choose a bracket. This bracket is going to have a lower interval, it's going to have an upper interval. So you choose a bracket AB, where A is the lower end of the bracket and B is the upper end of the bracket. As you choose this bracket, you make sure that this function f of x actually has an answer inside this bracket. It crosses the x-axis within this bracket you have chosen. So if that's the case, then you can start shrinking the bracket. Okay, you can start making the bracket smaller and shrinking smaller and smaller. You can start making the bracket smaller until it's small enough that the a and b actually hug the function where it crosses the x-axis. This kind of a method, this bracketing method which we're talking about here, is what is referred. There are other bracketing methods, but this one which we're talking about here is what you're going to look at. Basically, is something referred to as a bisection method. So there are other types of bracketing methods, but the one we're actually going to look at in this course is something referred to as as bisection method. So basically, that's how bracketing methods work. So you make an interval, then as you make a bracket, then you make sure that this particular function passes through this bracket. Then after that, you start shrinking the bracket. You make the bracket smaller and smaller and smaller, as you are going to see. The other ones are open methods. The other type of solutions is an open method, and this open method basically does not involve the use of brackets. With an open method, You come up with some function, then you come up with some function called an open method, or then you choose a guess value. You choose a value of x which is closer to the root. Then you put this value of x in this function, this method, open method thing, equation. This open method equation, when you let's say you choose a value of x, then you denote that value of x as x naught. Then you get this x naught, then you put it in this open method. This open method is going to spit out another value of x. But this value of x that you're going to get, which you're going to call x1, is going to be closer to where the function cuts the x-axis. After you get your x1 is not going to be the actual answer. You get this x1, you put it back. It's like I don't know what I can say. It's like an example where you, if it was possible, okay, if it was possible, like you eat something, then you go to the toilet, you get whatever, after you use the toilet, then you get something better. Then you get that whatever you've got from there, then you eat it again, then it gets better like that. So the solution you get, you put it back in an open method, then you get a better solution. Is that clear? On what an open method does.
Yes.
Yeah. So you start out with some guess value. Then this guess value x naught, you put it in the open method, then your open method is going to give you, hopefully, sometimes it's not always the case, hopefully it's going to give you an answer, a guess value which is better than what you started with. Sometimes when you put some of these solutions, if you have chosen a bad guess, then you end up having your open method can give you something which is further away from, which is worse than what you started with. So hopefully when you have a solution, then a guess value, then you put it in the open method, what you're hoping to do is you're hoping to get a value of x which is better than what you had. So it should be taking you closer to the answer, to what the actual answer is. Then you get your x1, you put it back again, then you get x2. Then you get x2, you put it back in the open method, you get x3. Then you get x3, you put it back in the open method, you get x4. Then you get x4, you put it back in the open method, you get x5. So it works like that. So you have got some value, you put it in the open method like that. So you keep on repeating this whole thing. And the open methods, the two open methods we're going to look at, there are a lot of these methods. There are a lot of bracketing methods. There are a lot of open methods, but we're only going to look at one bracketing method. We are only going to look at two open methods. So the ones we're going to look at are Newton-Raphson method, and the other one is what's referred to as a second method. Okay, so these are the ones which are easier for now. Hopefully next year we'll look at something else also, some other maybe two methods and stuff like that, so that you have good variety, because most of these things don't work all the time. Otherwise there will be no need for having so many of them. Okay, so bracketing methods and open methods have got advantages and disadvantages. With bracketing methods like bisection, any bracket method basically, as long as you have chosen a bracket where in between these brackets the function cuts the x-axis, your bracketing methods, as you shrink the brackets, will always give you a solution. So as you make the bracket smaller and smaller, as long as the function has cut through the bracket, as you make the function smaller and the bracket smaller and smaller, you end up having an answer. However, if you choose a bracket which does not hug the function, no matter how many times you try, you will never get the answer. So when it comes to bracketing methods, the first thing you have to make sure is that the function actually passes through this bracket. That's the first thing you have to do. You always have to check and make sure that this particular function you're interested in, it will actually pass through this bracket. If the function does not pass through the bracket, no matter how many times you shrink the bracket, make it smaller and smaller and smaller, you will not get the answer. Are we clear?
Yes, sir.
Yeah. So that bit you have to be aware of. Before you start, you have to make sure that you are sure that this bracket has got a solution. These days, because of languages like Python, it's easier to make a graph. So you can quickly make a graph and see whether this particular function passes through this particular bracket. Previously, that was not the case. You just had to do a particular check, and we still do such checks, okay, so that you can confirm the thing. So for a bracketing method, because you keep on shrinking the bracket bit by bit, usually they tend out to be slow. Okay, so bracketing methods are a bit slower. However, because computers have become faster and faster and faster, I don't think you're going to notice the slowness really. It will be, if you're using Python and other things, it will almost like instant just get the answer. So you will not really notice. But in reality, bracketing methods are always slower than their counterparts. So a bracketing method will always give you a solution, but they tend to be slow. When it comes to open methods, like the ones we're going to look at, Newton-Raphson method and also the second method, these can be fast. However, you might not always get the answer. So they're not very reliable, but they are fast when they work. Okay? When they give you an answer, they do it very fast. Okay? So with an open method, sometimes you will probably arrive at an answer. Sometimes it can take you away from the answer. So there is no guarantee that there's going to be convergence. It depends on how you've chosen your guess solution and also what kind of function you're looking at. So sometimes you might converge a solution, other times not so much. So basically these are the things you're supposed to get note of. If you are interested in speed, then you need to choose an open method. But if you choose an open method, there is a likelihood that either you get the answer very fast, or you might not actually get an answer at all. Are we clear?
Yes, sir.
Yeah.
Yes, sir.
If you want to get a solution and you don't really care very much about time, then you can use a bracketing method like bisection. And that's what you're going to start with. So we're going to start with bisection. We're going to look at 2 examples. Then after that, we'll move on to our open methods. So the question here is, as we do these steps here, as we go through the examples, you're going to see how the bisection algorithm is done. Okay. So example number 1, find the root of the equation f of x is equals to x to the power 5 minus 2, x to the power 2 minus 3 equals to 0. So basically, this function here, that's what you're looking for. And with the bisection method starting in the interval 0, 2. So this is the interval which you're looking for. Now, with what we have done, with the matplotlib we have done and how to plot graphs like that, we can actually have a look at what this particular function looks like in this interval 0, 2. So when you do that, basically this is what you have. This is the function you're looking at. So f of x is equals to x to the power 5 minus 2x minus 2x squared minus 3. So this is the function here. Now our interest is only in this interval 0 to 2. So from starting from 0 here to 2. And as you can see, this particular function there, it cuts the x-axis somewhere there. So with a simple plot of a graph, we can see that there is a solution to this particular function in this interval we have chosen. Are we clear? The solution is where this function cuts the x-axis, here at 0. Here, where f of x is equals to 0, here, there, where it cuts the x-axis. That's the solution. Is that clear to everyone?
Yes, sir, it is.
Next, the assumptions we made. We made the assumption that there should only be one solution. So in this interval we are interested in here, between 0 and 2, as you can see, there is only one solution there. And this solution which is there is not a complex number. It is actually a real solution. So the assumptions we have made are satisfied, that there should only be a single valid solution, and also that this solution should be a real solution. So, how do you know that the function actually has a solution in this interval? Well, I've just said it, where it cuts the x-axis. Now, what is happening when a function cuts the x-axis? Like in this case, you can see before we reach where it cuts the x-axis here, f of x is negative at f of x equals to 0, f of x equals to 0.5, f of x equals to 1. So you can see your f of x is a negative valued function. Do you see that?
Yes.
Then after this, where it cuts the x-axis exactly here, after that, f of x becomes a positive valued function. So f of x changes from being a negative function to a positive function after it crosses the x-axis. This is the criteria we use to find out if there is a solution between a bracket. You look for what is the value of the function at the lower end of the bracket and what is the value of the function at the upper end of the bracket. Since in this bracket there is only supposed to be one solution, you find out what's the value of the function at A, you find out what the value of the function at B. If the value of the function at A is positive and the value of the function at B is positive, then it means that throughout this bracket, the function is negative. Now, in this case, the value of the function at A is negative and the value of the function at B is positive. It means that the function has somehow crossed the x-axis. Are we clear?
Yes, sir.
So we do a check. We do a check of whether the function has crossed the x-axis or not. And this is how we proceed. So with our brackets being equals to 0 and 2, we write it like this. AB, which is A for the lower bracket, B for the upper bracket, AB, that is our bracket 0, 2. In this case, our A, the lower end of the bracket is going to be 0, and the upper end of the bracket, B, is going to be 2. So what we want to do here is we want to check if this particular function actually has an answer within this bracket. So for you to do that, you have to evaluate, or you have to find out how much the function f is at A and how much the function f is at B. So you have to find f of A. So f of A is going to be equal to f of 0, which is going to be 0 to the power 5 minus 2 times 0 to the power 2 minus 3, and this gives you minus 3. Minus 3 is a negative number. Okay, so at f of A, our function, so the information you get here is that at f of A, our function has got a negative value. Is that clear?
Yes.
Then you go to B. You also work out f of B. F of B is going to be equals to, that is f of 2, which is going to be 2 to the power 5 minus 2 times 2 to the power 2 minus 3, and this is going to be 21. So at f of B, our function is 21. 21 is positive. So at f of B, our function is positive. It's a positive valued function. So at f of A, it's negative. At f of B, it's positive. So that shows you that the function has crossed the x-axis somewhere in between here. It doesn't say exactly where, but it just tells you that in between A and B, the function has crossed the x-axis. Is that clear?
Yes, sir.
So how do you actually do this? After you find f of A and f of B, so you work out this product. You work out the product f of A times f of B. So you work out the product f of A times f of B. Now, if this product f of A times f of B is greater than 0, meaning that it's positive, then there is no solution in between 0 and 2. If it's positive, it means one of two things. Maybe f of a is positive and f of b is positive. So positive times positive gives you a positive number, which is greater than 0. Or it can be negative, f of a is negative, f of b is negative, f of b times f of a, negative times negative gives you a positive. That in either case is telling you that the function has not crossed the x-axis. Are we clear? So when you multiply after you work out f of a, which is minus 3, then you multiply f of a times f of b, which is 21. What you get, if it's greater than 0, then it tells you that there is no solution in the bracket you have chosen. But if you multiply f of a times f of b, then it gives you a negative product. Then it means that the function crossed the x-axis. If the function crossed the x-axis, then it means that a root exists in the bracket you have chosen. One root exists. Are we clear?
Yes.
So this is how you check. So the first thing when you choose a bracket, you are choosing a bracket, or when you are given a bracket, when you're given a bracket, you have to confirm if in this bracket you have chosen, the function you're looking at actually has a root. Does it cross the x-axis? So in this case, f of a, work out f of a times f of b, which is going to be minus 3 times 21. This is going to be minus 63 or negative 63. Negative 63 is less than 0. So it's negative. So this means that our product f of a times f of b is negative. If your product is negative, then it means that there is one root. A root exists in this interval. Are we clear?
Yes.
If there is a root existing in an interval, then the next thing we need to do is, with bisection, what we do is we now try to find a guess root. Okay, we try to find what is the root. So we guess what the root is. And how do we guess what the root is? We work out something called a midpoint. A midpoint C. And how do we get the midpoint? Well, we just add a plus b, then we divide by half. Whatever a is and b is, we add a and b, then we divide by half, so that we get our C. So in our case, our a is 0 and our b is 2. So our midpoint in this case, C is going to be equal to half. 0 plus 2, that's going to be 2, and 2 multiplied by half, that's going to give you 1. Are we clear?
Yes, sir.
Now, after you find the midpoint, the next thing you do is you want to find out what is the value of the function at the midpoint. This, you want to work out this. You want to work out f of c, which is equal to f of 1. What is f of 1? What is f of c? So in this case, f of 1 or f of c is going to be equal to 1 to the power 5 minus 2 times 1 to the power 2 minus 3, which is going to be minus 4. So you have found the midpoint. So there is a, and we know that f of a is minus 3, right? Here, f of a is minus 3. It's negative. Then we have found the midpoint, which is f of 1. F of 1 is also negative. It's minus 4. Then we have f of b, which is 12. So in between a, c, so f of 1 is here. The midpoint is here. So our midpoint is here. C is equal to 1. That's where our midpoint is. So we have 0 this side. We have got 2 this side. Then we've got a midpoint, 1, which is here. So our function at f of a, which is 0, is minus 3. At the midpoint, it's minus 4. Then at b, it's 21. So you can clearly see that our function between the midpoint and A, it's negative. Between here and there, the function has not crossed the x-axis. Do you see that?
Yes, able to see.
Yeah, the function hasn't crossed the x-axis. So you carry out a check. You ask yourself, you carry out a check. After you find C, the midpoint, then you find the value of the function at the midpoint. You carry out a check where you ask yourself, has the function crossed the x-axis between A and C? Or in other words, is there a solution to this function f of x between A and C? And how do you do that? How do you carry out the check? You multiply f of A times f of C. Why are we doing the multiplication? We're doing the multiplication because of the other thing we did earlier. We know that if you multiply the value of the function at A and the value of the function at C, if it comes out positive, if the product comes out positive, then it shows that there is no root between A and C. If the product comes out negative, then it shows that there is a root between A and C. Are we clear?
Yes, sir.
So we check between A and C, is there a root? So in this case, you carry out this product, f of A times f of C. So f of A is minus 3, f of C is minus 4. So minus 3 times minus 4, this is going to give us 12. 12 is greater than 0, so this is positive. So this means that between A and C, there is no root. Since f of A times f of C is positive, it means that between A and C, there is no root. Are we clear?
Yes, sir.
If there is no root between A and C, then we can make C become our new A. We shrink we move the lower bracket A, which was at 0, we move it to C. That's how the shrinking is done. Are we clear?
Can you repeat that point again?
I am saying that if there is no answer between A and C, remember AB is our bracket, right? It's big. But if between A and C there is no answer there, then we can move A so that A becomes C. Because between A and C there's nothing there.
Yes, sir.
Yeah, so we make the lower bracket, we shift it up. So our C is going to become A. So A is now going to be 1. So our C, which is equals to 1, will now become A. So that A becomes 1. And the value of the function at C, which is minus 4, that is going to become now our f of A. Are we clear?
Yes, sir.
Yeah. So with this change, our bracket has become smaller. Instead of being AB, which is equal to 0,2, now our A is 1. So now our bracket, instead of being 0,2, now our bracket is going to be 1,2. 1,2 is basically, our bracket is going to be between this one here and the 2 here. Previously it was from 0 here to 2. Now it's just going to be between the 1 here, this is going to be the lower end of our bracket, and the 2, which is this side. Is that clear?
Yes, it is.
Okay, so that now, since our bracket is now smaller, now we have got a new bracket, 1,2. With this new bracket, 1,2, we know that the answer is between 1,2. We calculate a new midpoint using our new A and B. We work out a new midpoint, C, using our new value of A, which is now 1, and our odd value of B, which is 2. So our midpoint C is going to be equal to half A plus B. Remember, your midpoint C is your guess solution. The midpoint is the solution. So we had a first guess solution of 1. Now we are going to work out another solution. So C is equal to half A plus B. Our A is 1. Our B is 2. So in this case, C equals to half 1 plus 2. That is 3. 3 divided by half, that is 1.5. So you get your C as 1.5. So this is the solution, C, 1.5. 1.5 as the solution between, as the midpoint between 1 and 2. So there. There. After finding our midpoint as 1.5, the next thing you do again, you want to find out what is the value of the function at this new midpoint you have. What is f of c? So in this case, f of c is going to be equals to f of 1.5. So that's going to be f of c, which is equals to f of 1.5. It's going to be 1.5 to the power 5 minus 2, 1.5 to the power 2 minus 3. This is going to give you 0.09375. That is the value of the function. As you can see, this particular function at f of c is positive. It's 0 point something, but it's greater than 0. Are we clear? This value is a positive value, 0.09375. It's positive. It's no longer 21. Well, sorry, it's compared to 21, but this is a positive value here. So the next question after you find this midpoint and its value, we ask the same question you have asked. Is there a solution between A, our new A, and our new midpoint? Between A and C, is there a solution between A and C? Are we clear? We ask the solution, yes. Is there a solution between A and C? So how do we find if there's a solution between A and C? We work out this product. We work out f of A times f of C. When you work out f of A times f of C, if this product turns out to be positive, then there's no solution. But if it turns out to be negative, then we know that there's a solution. So f of A multiplied by f of C, f of A in this case is minus 4 multiplied by f of C, which is 0.09375. You multiply this times that, you get minus 0.375. This is a negative 0.375. This is negative. It's less than 0. Are we clear? Since our product f of A times f of C is negative, this means that between A and C, our function cuts the x-axis. So there is a root between A and C. This. Are we clear?
Yes, sir.
But if there is a root between A and C, as you can see, A is here, A is 1, C is 1.5 there. So if there is a root between A and C here, it means that between C and B, this side, there is no root. Do you see that? If between A and C there is a solution, then it means that between C and B there is no solution. Is that clear?
Yes, sir.
So if between C and B there is no solution, then we can make our C become B. So we shrink the B so that the B becomes C. So we make our bracket smaller. So if that's the case, if there is a solution between A and C, then our B, we can make our C become B here. Our C, which is equal to 1.5, we can make our C become B. And we make our f of C, which is equal to 0.09375, become f of b. Is this clear? We are only interested in the places where there's a solution. So if there is a part where there's no solution, we discard it. Then we make that midpoint become the new b. Or we make that new midpoint become the new a. Is that clear? Is it clear?
Yes, it is.
Okay, so now that we have done this, we have made our midpoint become C. So our bracket will now shrink. Our bracket, which is AB, will now shrink to 1, 1.5 instead of 1, 2. So our bracket is becoming smaller and smaller. So now that we have, after shrinking our bracket, we are also going to work again. We'll work out a new midpoint. A midpoint is your solution. So now we're going to use our odd A, which is equal to 1, and our new B, which is equal to 1.5. So that we work out between 1 and 1.5, we work out a new midpoint. The midpoint C is equal to half A plus B. So in this case, C is going to be half 1 plus 1.5. 1 plus 1.5 is going to be 2.5. 2.5 divided by half is going to give you your 1.25. So 1.25 becomes a new midpoint. 1.25 is somewhere halfway here. This is 1.5. So 1.25 is somewhere halfway there. So that's where your midpoint is going to be. With this midpoint, C equals to 1.25, you check if your function at 1.25, you check what the value between C, which is 1.25, and A, which is 1, whether the function crosses the x-axis. And how do you do that? The first thing you have to do is you need to find out what is the value of the function at the midpoint. So f of C is going to be equal to f of 1.25. So in this case, f of C, which is equal to f of 1.25, is going to be equal to 1.25 to the power 5 minus 2, 1.25 to the power 2 minus 3, and this is going to give you minus 3.073242188. The point here is that it's negative. So at the midpoint, the function f of x has got a negative value. If the function f of x has got a negative value at the midpoint, then you check between A and C. You always check between A and C. If there is a solution between A and C. Now we know by working out this product, f of A times f of C. Now in this case, we know that f of A is 1. C is 1.25. So f of 1 is minus 4, and f of 1.25 is what you have just found out here. So here, this one, minus 4 is negative, multiplied by minus 3.07, that this is also a negative value. You multiply these, you end up with 12.29298675. This is a positive value. This positive value is greater than 0. Since the product f of A times f of C is now positive, this is telling you that there is no root between A and C. Are we clear?
Yes, sir.
If there is no root between A and C, then you can make your C, which is the midpoint, you can make it become A. This, your C, which is equal to 1.25, you can make it become A. And the value of your function at C, which is equal to minus 3.073, whatever it is, this is, you can make that become f of A. So when you do this, then your bracket is going to shrink. So now you're going to have a new A and a new B and B. So f of A, f a b, so that's going to be, your A is now going to be 1.25 and your B is going to be 1.5. Are we seeing the process and what you're doing when you're doing bisection? So now we have a bracket at 1.25 and 1.5. So basically, when you go to your graph, your bracket is now between here, 1.25 and 1.5. So it's becoming smaller and smaller and smaller compared to where we started from. Is that clear? Are we clear? Any questions?
It's clear.
Now, you notice that you're making progress, but you are making the progress very slowly. And that is one of the handicaps of bisection. If we keep on doing this, we will get the answer eventually, yes, but we're going to get to the answer very, very, very slowly. Is that clear?
Very clear, sir.
Yeah. So bisection is not supposed to be your number one choice method. You only use bisection when the other methods will not work. The faster methods, when the faster methods don't work, then this is your last method to go to. Because bisection will always give you a result as long as you have chosen the bracket properly. So next we work out a new midpoint using our A, which is 1.25, and our B, which is 1.5. So C is equal to half A plus B. So in that case, C is going to be equal to half 1.25 plus 1.5. This is going to give you 1.375. So this is going to be your new midpoint, 1.375. At this midpoint, 1.375, the next thing you want to do is you want to find out what is the value of the function at this midpoint. So f of c, which is the value of the function at the midpoint, f of 1.375, that's what you have here, f of c, f of 1.375 is going to be 1.375 to the power 5 minus 2, 1.375 to the power 2 minus 3. This is going to give you minus 1.8 minus 1.866363525. This is a negative. So the function at this new midpoint has got a negative value. So you've got a midpoint, C, which has got a negative value. You've got your A, which is 1.25, and at 1.25, your function is also negative. So you check, is there a solution between A and C? And how do you do that? You work out this product, f of A times f of C. So f of A times f of C, f of A is this. This is your f of A. It's a negative number, minus 3.073 something something. Then your f of C is this one here, minus 1.866 something something, which is what you have here. So you are multiplying some negative number times some negative number. Negative times negative is going to give you a positive number, which is 5.73 something something. This is positive, it's greater than 0. Since this product f of A times f of C is positive, it's telling you that there is no solution between A and C. Are we clear?
Yes, it's clear, sir.
Since there's no solution between A and C, you can make your C, which is 1.375, become your new A. And you can make your f of C, which is minus 1.8 something, become your new f of A. When you do that, then your bracket AB is now going to become it's going to become 1.375, 1.5. It's going to become smaller than it was. Again, we work out a new midpoint based on this adjusted bracket. So our new midpoint, C, is going to be equals to, our A is now 1.375, our B is 1.5. So your C is going to be equals to half A plus B, like that. Then you work out your C equals to half 1.375 plus 1.5, and you end up with this 1.4376. This is your new midpoint. After finding this midpoint of 1.4376, then you want to find what is the value of the function at this midpoint. You want to find out f of c. So f of c is going to be equal to f of 1.4376, like this. So f of c equals to f of 1. That's going to be 1.4376 to the power 5 minus 2, then 1.4376 to the power 2 minus 3, and you're going to get the value of the function at the midpoint as minus 0.994637489. This is negative. Are we clear? Our A is 1.375, and the value of the function at A is minus 1.8. It's negative. So at our A, the value has got a negative function. At our new midpoint you have worked out here, f of c, the value of the function is negative. So we check if there is a solution to this function between A and C by working out this product f of A times f of c. So f of A times f of c, that's going to be minus 1.866 36 that, then times minus 0.99468 that and stuff. Basically you're multiplying a negative number times a negative number. If you multiply a negative number times a negative number, what you're going to get is a positive number. This positive number is greater than 0. Since your product f of A times f of c is positive, it means that between A and C there is no root. Are we clear?
Yes, yes.
If there is no root between A and C, then you can make your C, your midpoint, which you have worked out as a root, you can make your C become A. And the value of the function at this midpoint C, which is minus 0.99, you can make that become the value of f of A. So in this case, now you're going to have your bracket having shrunk further. Now your A and B is going to become 1.4376, 1.5. So this is going to be your new bracket. You keep on doing this. The other thing you notice is that if your bracket is too big, it means that you have to do this more. It's more time consuming to do. So you need more steps, more repetitions. So you always have to start with a bracket which is fairly small. Even in our case where we started with a bracket of 0 to 2, you can see how many steps we have gone through. Okay, so now our bracket is 1.4376, 1.5. So we work out a new midpoint. C is equal to half A plus B. So that's going to be C is equal to half 1.4376 plus 1.5, and this is going to give us 1.4688 as our new midpoint. So our new midpoint is 1.4688. Like that. Next, we want to find what is the value of the function at the midpoint. F of c. So f of 1.4688. That's what you have here. F of 1.4688. That's going to be 1.4688 to the power 5 minus 2 times 1.4688 to the power 2 minus 3. This is going to give us minus 0.478569577. This is a negative function, negative valued function at the midpoint. So our function f of x has got a negative value at the midpoint. If it has got a negative value at the midpoint and our a, in this case our a is 1.4376, and this 1.4376 has got a negative value at a, this function has a negative value at a, we can check if our function between a and c has got a solution by working out this product. So we work out f of a times f of c. That's going to be this, the value of the function at a, which is negative, multiplied by the value of the function at c, which is also negative. So we're multiplying a negative number times a negative number, then we get a positive. This positive is greater than 0. So basically, when you get a product of f of a times f of c, which is greater than 0, positive is telling you that there is no solution to this particular function between a and c. If there is no solution to the function between a and c, then you can make your midpoint, which is c, become the new a. because between A and C there's nothing there. So you can make your midpoint C become the new A. So our A becomes 1.4688, and the value of the function at C, which is f of C, which is minus 0.478 569,557, becomes our f of A. Are we clear?
Yes, it's clear.
Yeah. So with that bit, then our bracket now shrinks again. So our AB becomes 1.4688, 1.5. So you can see our bracket has become smaller and smaller and smaller. So somewhere between 1.4688 and 1.5, this function you've been looking at cuts the x-axis somewhere in between there. So this is an example. Again, you proceed to work out the midpoint C. So in this case, you've got 1.468, which is your new A, and your odd 1.5, which is this. So you work out your C, and C is going to be half A plus B, so that's going to be C equals to half 1.4688 plus 1.5. You're going to get your 1.4844. So this is going to be your midpoint. Then you try to find out what is the value of the function at this midpoint. So in this case, the value of the function at f of 1.4844. So f of 1.4844, that's going to be 1.4844 to the power 5 minus 2, 1.4844 to the power 2 minus 3. It gives you minus 0.199883296. This is the value of the function at the midpoint. It's negative. Since the value of the function at the midpoint is negative, and the value of the function at A, the value of the function at A is this one. It's also negative. So with the value of the function at A being negative, with the value of the function at the midpoint being negative, you work out this product. You want to find out if there is a solution to this function between A and C. So your f of A times f of C, your f of A is negative. This is what it is, a negative number, multiplied by your f of C, which is also a negative number. You multiply them, you end up negative times negative, you end up with this guy, which is a positive number, 0.09565806, which is positive, greater than 0. This positive number shows that this positive product, f of A times f of C being positive, is showing you that there is no solution between A and C. If there is no solution between A and C, then you can make your midpoint C, which is equal to 1.4844, become your new A. And the value of the function at C, at f of C, which is equal to minus 0.199883296, you can make this become your new f of A. So your bracket is now going to shrink to AB equals to 1.4844, 1.5. It's becoming smaller and smaller, very small. If at this point you still want to work out a new midpoint, that's fine. You now have your A, which is equals to 1.4844, and your B, which is equals to 1.5. So you work out your midpoint here. C is equals to half A plus B, so that's going to be C is equals to half 1.4844 plus 1.5. So you end up having 1.4922. So you got 1.4922. This is your new midpoint. So the bracket now is very, very thin. You work out the value of the function at this midpoint at 1.4922. So in this case, f of 1.4922, that's going to be 1.4922 to the power 5 minus 2, 1.492 to the power 2 minus 3. This is going to give you minus 0.045966,478. This is negative. So at this particular point, the value of the function is negative, and at the midpoint is negative. Then you look for if there is a solution between A and C. So you work out this product f of A times f of C. Now f of A, that's what we have here. Your A is now 1.48 1.4844, and at f of a, this is the value of the function. It's negative. And we have just found out that our f of c also is negative here. So you multiply f of a times f of c, then you're going to end up with this negative number multiplying another negative number, so you end up with a positive number again, which is greater than 0. So this is telling you that between a and c, there is no root. Are we clear? Now that our bracket is okay, there's still something. Okay, so in this case, you make your
This is clear.
yeah, you make your midpoint c, which is equals now 1.4922. You make your midpoint c become a, and you make the value of the function at the midpoint, which is equal to minus 0.054966 you make this become your f of a. Midpoint is very small now, but I think you can make one more guess. Okay, yeah. So this is what our midpoint is now. AB is equals to 1.492, 1.4922, 1.5. So this is your midpoint. Now, after you come up with this last bracket, which is very, very thin, because it's 1.4922 and 1.5, now you work out your final midpoint using A and C. So in this case, your C is going to be equal to half A plus B. So this midpoint you're going to work out is going to be your final solution as the final root. So this is going to be C is equal to 1.4922 plus 1.5, which is going to give you 1.4961. And which is this? This is going to be a root. Then you try to see if this solution you've come up with, if it's going to make your function almost equals to 0. So you work out f of c, which is equals to f of 1.4961, which is equals to 1.4961 to the power of 5 minus 2 times 1.4961 to the power 2 minus 3. This is going to give you 0.018912834. This is what you get. As you can see from the root we have found, it is not exactly equals to 0. Your root you have found of 1.4961, when you put 1.4961 in the function f of x, it does not give you f of x equals to 0, but it gives you something which is very, very close to 0. So f of x is approximately equals to 0. Is it clear?
Yes, it is.
That is why these methods like this, where you go through these steps, like we have done with bisection, these methods are also called approximate methods. They give you an answer where it's not possible for you to find an exact answer. Sometimes it's possible for you to find an exact answer, but maybe you don't know how to do that. So you can give an approximate solution. So if you're giving an approximate solution, your approximate solution in this case is going to be 1.4961. Are we clear?
Yes, it is clear, sir.
Now, the other thing I want to point out, as you can see, we have spent the whole lecture doing this same method. So during the test or during an exam, I'll tell you, work out only maybe 3 midpoints or 4 midpoints. Because right now, I think what we have is about 8 midpoints. So I'll tell you, work out the first 3 midpoints or work out the first 4 midpoints. Using the first 4 midpoints, then give me an answer. Or I'll tell you, sure that the midpoint C0, the first one, or C1, the first one is this, C2 is this one, the first midpoint, the second midpoint is this value, the third midpoint is this value, the fourth midpoint is this value, like that. Are we clear?
Yes, it's clear.
Okay. If there are no questions for today, we stop here. We'll continue tomorrow with example number 2. Also, if you're not aware, the notes are already on your Moodle, so you can download the notes from your Moodle and you can print them and you can have a look at them. Where there's a problem you don't understand, you can point out something later on in class. So we stop here today. The upload will be made available on YouTube